In this video I am going to derive the EMF equation of a synchronous machine or synchronous generator. So before deriving the EMF equation, so this is a specific approach which I will follow, and I will try to develop the equation from the case study. So the first thing which I would like to derive is I would like to derive two important components which is known as the breadth factor and pitch factor. So if I will name this as KB and this as KS, then my winding factor KWF is equal to KB into KS. This is known as my winding factor. And one other important thing is there is a assumption that the magnetic circuit is linear. There is no harmonics or transients in the system. The system is stable. So this is an assumption which I am going to take while I am going to make the derivation, and this is only a approximate derivation. To give an understanding. So this is only an approximate derivation intended to give an understanding of process of getting to EMF or the approx equation of EMF. So these are some of the things which I want to highlight, and again one thing which I want to make an assumption is that the machine is operating at synchronous speed. So F is equal to given by 120, or the synchronous speed is given by ns is equal to 120 F by P, and the frequency here considered is equal to 50 Hertz for the EMF generated, and again it is a three-phase machine and it's a two-pole salient pole machine. The field is DC excited. So these are some of the assumptions which I want to consider while doing the derivation. So the next step is that, so again all the values, so the figures used here are figures are only for approximate derivation or to demonstrate. So coming to the next point is that drawing a simple alternator. So this is the core, so which is again not very symmetric. only to give understanding. So if we are considering that there are three phases, so if this is my phase A and this is my phase A dash, and at if you can see this arrangement which is like this. So if you are assuming the poles of the magnet to be in this way, in this position, which is just drawing a approx figure, so this is a south pole, and if this is a north pole, then this is what is my q axis and this is what is my magnetic axis. Also this will form the axis of the field for A. So this is a long derivation, but if you go through the videos you will get end-to-end idea of the process followed. So this is my phase B dash B and this is my phase C dash C. So I would use to write some values which I can keep. So the first thing which you is that the phase difference between the voltage is given by lambda is equal to the phase difference between the voltage is given by 2 pi divided by m, where m is equal to the number of phases. So this is equal to 2 into 180 divided by 3, which is equal to 120 degree. So my voltage is EA, EB and EC, which is being generated in the phases are having phase difference of 120 degree. Also each of these coils are placed 120 degree apart from each other, and if I am considering this as my phase A, then if alpha is equal to given by phi p by s is equal to phase angle between EMF of each coil in a phase. So if this is a EMF generated E1, this is a EMF generated E2 and this is a EMF generated E3. So the phase difference between E1, E2 and E3 will be what is known by alpha, and alpha is equal to 5 into 18 or 5 into 2 divided by 18, which is equal to 20 degree in this case, and my alpha into m, where m is number of phase, is equal to 60, is what is known as my phase spread. So now the first is the derivation for the breadth factor KB, which is equal to the ratio of voltage generated due to phase spread, since each voltage having a different voltage generated in each of the coils or coils of a phase which are eventually connected in series. So it is assumed that the voltage generated in E1, E2 and E3 in this case, which is for phase A, are connected in series. Divided by the voltage generated if there was no phase spread. So this is what is known as my breadth factor given by KB. So since considering all the values which we have so far, that this is a two pole alternator, there is 18 coils, that is 6 per phase, and in this 6 per phase, 3 is per pole per phase. So this is how my generator was, and my alpha is equal to the phase angle of the voltage generator was 2 pi by 3, which is given by 120 degree, and my gamma was 120 degree, and my alpha was equal to pi divided by P into S, which is equal to 20 degree, and my phase spread M gamma was equal to 60 degree, which was equal to my phase spread. So if I am drawing a phasor of each of the voltage generated, and if I am considering it graphically, it's possible to validate the same thing graphically, as my each of the voltage E1, which is generated for only phase A, I am considering here. So the E1 voltage which is generated for one of the coils, and the E2 which is generated, and the E3 which is generated. So each of this will be separated by what is known as a 20 degree. So if I am drawing it using the vector, then it's possible to draw these three, and whatever resultant or the addition which I will get will be my phase voltage which is generated in the EA. And if I am considering this whole graph with a reference point origin, and if I am saying that this is my P, Q and R and S, then if I am dividing this graph with a midpoint, then it's possible to see that whatever is your, and if this is what will be equal to my M gamma is equal to my phase spread, and this will be equal to M gamma by 2, and this will be equal to M gamma by 2, or M alpha by 2 in this case. Now so it's simply possible to say that if you are having these two vectors, and if you are projecting it onto the x-axis, what you will get for this whole distance is equal to your EA is equal to 2 PQ of sine of M alpha by 2, and if you are having this voltage PQ, so 3 times PQ was equal to your voltage. So this 3 times of PQ is equal to, if you are having this as 3 times, if you are going, then this would have been your voltage without any distributed winding. So if if you would have this core, and if all of your winding was located in a single coil single coil of A dash having two turns, and if this was the case, then the voltage generated would have been equal to 3 times PQ. But since you are having a distributed winding, the voltage generated is not equal to 3 times PQ, and it's equal to what is given by this value. So it's mathematically possible to take a value of E1 is equal to, suppose you say that E1 is equal to 2 centimeter and your alpha is equal to 20 degree, and it's possible to mathematically draw this graph and validate whatever I am saying here, which I have already done for this case. So you can, if you want to validate this, then you can say that if each of the voltage generated in each one of the coils is 2 centimeter, if you are drawing it in the graph, which is taking 1 centimeter is equal to 10 volts or 100 volt, then you can easily validate that. So again, it's possible to have a midpoint here in such a way that this is equal to m alpha by 2, or in this case where this is equal to alpha, only alpha by 2, only for this area, considering that this is alpha. So what you will get is, you will get this as something like 3 times of PQ sine alpha by 2, and this is equal to what is your 3 times PO, sorry, this is again PO, so this is 3 times of what is your PQ. So my KB is equal to PS from the graph divided by 3 times PQ, and if you are substituting it, it will be equal to what is 2 times PQ of sine of m alpha by 2 divided by 3 times PQ of sine alpha by 2, and this gives my KB as equal to sine m alpha by 2 divided by sine alpha by 2, which is equal to what is known as my distribution factor or breadth factor. So I have found what is my, so for this case, if I am erasing all this, what I have found is, I have found my breadth factor now. Breadth factor as KB is equal to sine of alpha by 2 divided by m alpha by 2 divided by sine of alpha by 2. The next step is finding what is known as the pitch factor. So it's possible that considering the phase of A, that if I am having a north pole and if I am having a south pole, and if I can show my coil as placed in this way. So this is one of my coils, and if this is a coil which was producing the E1 voltage in my case, then there would be a current or voltage E1 produced in this way and voltage E2 produced in this way, and the distance between these two is equal to phi or 180 degree electrical angle, which is known as my pitch between the two coils. So again, if it is possible to see that whatever voltage E1 was generated, so if I am saying that this is EC1 and this is EC2, so whatever E1 which was generated was equal to EC1 plus EC2. But now if you are having a winding which is known by what is known as a short pitch winding, that if you are for some reasons which is you are reducing the pitch by a factor like alpha or beta for to say, so and this is phi minus beta, then it is seen that whatever voltage which will be generated in this, so if it was both of it was generated in this way, whatever if and now this is moved a little bit here, so whatever voltage will be generated with a slight angle or slight phase difference from this by the pitch factor which is beta, so or the pitch angle which was beta. So it next is to find the pitch factor given by kph, which is equal to the ratio of voltage at full pitch and voltage at short pitch. So this is equal to whatever was my voltage when it was full pitch was equal to E1, and now when it is short pitch, there will be a phase difference which can be given by the same voltage EC2 will now have a angle of beta, which is, and this will be what will be my E1, and this will be what is my angle of beta by 2. So in this case E1 is equal to 2 of 2 E1 sine beta by 2, which or 2 EC1 sine beta by 2. So again this is equal to 2 EC1 sine beta by 2 and divided by E1. So my E1 is equal to 2 EC1. So this equation, if I am substituting it, my pitch factor will become equal to sine of beta by 2, and now what you have found out is you have found out what was your pitch factor. So one important thing to know is that your pitch factor kph will be given by sine of beta by 2, where beta was your angle by which angle of pitch reduction in this case. So your kW is given by kb into kph. This together is known as what is my winding factor. So now the next step is to derive the EMF. So considering the same conductor which we are having, then it's possible to say that the EMF could be given by the equation of Faraday's laws of electromagnetic induction is equal to n d phi by dt. And if Z is equal to number of conductor in this case, and Z is equal to 2 times of the turns, then 2t will be equal to my n for this equation, which n is equal to the turns, number of turns of conductors. So this whole equation can be written as E is equal to 2t phi by t, where phi is equal to my flux per pole in Weber. And this will now have to be multiplied by P to give you the total flux in Weber, because this is flux per pole, and P is the number of poles. And now your n as synchronous speed is, or the rotation is given by in RPM. So based on whatever your speed was or the rotation, so time can be given by 60 divided by n, which will be give you the minutes. So based on that, it's possible to modify this equation is equal to 2t pi into p divided by 60 into n. Now your n is again is equal to 120 f by p, which is equal to the synchronous speed. Since this is a synchronous machine, this is an assumption which I took. So this whole equation will again become equal to 2t pi and into p into 120 f by p. So this is equal to divided by 60, which was the case there. So this will cancel and become equal to 2. So my E average, which is generated, equal to 4 f phi t, and your RMS can be given by multiplying the form factor kf, which is equal to 1.1 if you're considering the AC power, and your ERMS voltage will be equal to 4.4 f phi t. And when you are adding your winding factor, you will get the actual voltage which you are getting if you are having a distributed winding. So this is how to derive for the RMS value. So these are all the values which we derived, and it's possible to mathematically vary or graphically verify for the finding out of the breadth factor, finding out of the winding factor, And it's even possible to mathematically verify for this if you are taking a specific design case of a machine where you are having a specific value of flux per pole and number of conductors and the synchronous speed given, then it's possible to verify for the voltage which you are getting here. So this is how to approximately derive for the RMS value of voltage generated in any phase. So this is ERMS per phase which is generated, which can be given by this equation.